All right, we're going to look at calculating the probability of events um, without replacement occurring between the two events. And without replacement, would look a lot like, taking a deck of 52 cards, taking one card and keeping it, and then you've got 51 cards left in the deck. So what you'll notice is that the sample space has changed, right? So we had our original sample space, which was 52 cards. And then our sample space when we had without replacement during our second experiment, and that is 51 cards. So, certainly trying to calculate, a second event that occurs after the first one where a card was drawn and kept, this is actually creating a situation where the two events are dependent. Okay. The second event is certainly dependent on the first. Um, and in calculating the probability of two events where they're dependent, this is the form of the equation you're supposed to use. And technically, this conditional probability here, if you were to write it on its own, would be equal to the order of C intersect A all over the order of A. This is, the official definition of this. But, given this simple case here, I couldn't really find like an equation or a simple way of explaining this kind of dependent event, but using this formula here. So what I'm calling this is kind of like a special example of conditional probability where only the sample space is changing. All right, so let me maybe try and elucidate what I mean. So event A, we're going to say is the card the Jack of Hearts, and event C is the card Four of Clubs. So find the probability of getting a Jack of Hearts and a Four of Clubs, and this is assuming without replacement. I should have typed that in. So to calculate this probability, I mean, this would technically be the equation that we would use to calculate this probability of having both of these things occurring without replacement. But we can't think of this conditional probability being like that. Otherwise, it won't come out right. Instead, we got to think about this in a different way. So A is we're starting with a 52 card deck. So the sample space is going to be out of 52. Now, how many Jack of Hearts do we have? We've got exactly one. So the probability of getting a Jack of Hearts with our first draw is 1 out of 52. Now let's think about the probability of getting C. So the probability of getting a Four of Clubs given a Jack of Hearts came first. So regardless of whether we get a Jack of Hearts or not on the first draw, we're keeping that first card. So what's the probability then of getting a Four of Clubs if we've kept a card? Well, the sample space is going to shrink from 52 down to 51. And how many Four of Clubs do we have? Only one. So the probability of getting this card, a Jack of Hearts, keeping whatever card that first one was, and then getting a Four of Clubs second is 1 over 52 times 1 over 51, which comes up to 0.0377%, which is really small. So this is a special kind of uh, dependent events occurring. And the way that I think about this, is that you're starting with an original sample space, that's larger of 52 cards, and that ends up shrinking down to a smaller sample space of 51 cards. And that's because of the effect that the first event has on the one that follows it. The first event being taking a card and holding it without replacement. So what we see here is a similar example, and I'm going to go ahead and work this one through. So, here we're starting with a 52 card deck. We're not replacing a cards. A card is drawn and not replaced, then a second card is drawn. What is the probability that both cards are clubs? All right. Um, so in order to calculate this probability, we're going to have E is going to be that the first card is a club. Let's see here. And F is that the second card is a club. And we want to know what's the probability of E and F. Now, because we see that it's without replacement, this is going to be like the official multiplication rule equation we're going to use. But because of this style of question, we're not going to treat this conditional probability like we would in some other circumstances where we're going to think of it this way. Okay, this will end up garnering us a wrong answer if we do this. Instead, we're going to think of, this probability of F given E as the probability of F given E occurs first and affects conditions of F. All right, and try and think about what that's going to look like. All right, so we have our probability of E, which is going to be the order of E over the order of the sample space. And because we're taking a card and not replacing it, then we're going to have two different sample spaces. One sample space, which is going to have 52 cards in it. And then once we've kept it, we're going to have 51. Now we just have to think about what's going to be the order of E and the order of F. Well, E, what's the order of getting a club? Well, we come up here and we look at our clubs. This right here is event E. So how many do we have? We've got 13 clubs in the deck. Now, how do you account for maybe the second card being a club? Well, for the second card to be a club, you assume that the first one drawn was a club. So if you assume that the first card drawn was a club, then the order of our F isn't going to be of 13 clubs, it's going to be of 12. So not only did the sample size go down by 1 because we took a card and kept it, But because we're actually drawing two of the same suit, then the number in the suit is always also going down by one. So really a real simple scenario, but a simple scenario where you really have to think about it. Okay. And so to figure this out, this will be 13 times 12 all over 52 times 51. And that'll come out to 0.059, or the probability of E and F is 5.9%. All right. And before I guess I exit this one, this is the correct answer for this. What would have happened to this part had I done it this way? Okay, let me do that here as an aside. So probability of F given that E occurs first be the order of F intersect E all over the order of E. All right, so what is in this intersection between these two events? So we look up here, the intersection is actually going to be all of F, which is 12. And then what's the order of E itself? It's 13. Don't move on me. There we go. There we go. Okay. It's going to be 13. And so if we had instead put 12 over 13 instead of 12 over 51, that's going to change the nature of our answer. So we'd have 13 over 52. And instead of having 12 over 51, we had 12 over 13. The 13s would cancel. That would give us 12 over 52. And let me bust out the calculator really quick. So if I do 12 divided by 52, get 0.2308. That's rounding. So I get 23.08%. And so this answer is much different than that one. Okay. So this is why, this is a kind of like a special case where I want to use this terminology, the probability of getting a second club given a first club, because it makes sense to say it that way. But we can't use kind of like the strict rules of conditional probability here. We just have to think of it, in this case, more in like a common sense way in order to think about it as the sample space going down by one and the number of clubs available going down by one. All right. Let me know if you have any questions.